Introduction to Statistics, Chapter 5, Probability, Section 5.4, Conditional Probability and the General Multiplication Rule. Conditional probability. It is the probability that the event F occurs, given that the event E has occurred. The notation, capital P, parentheses F, vertical line E, parenthesis is read, the probability of event F given event E. Conditional probability rule. If E and F are any two events, then the probability of event F occurring given the occurrence of event E is found by dividing the probability of E and F by the probability of E. So here's the formula. Probability of F given E is equal to the probability of E and F divided by the probability of E. Or by dividing the number of outcomes in E and F by the number of outcomes in E. So the probability of F given E equals the number of outcomes in E and F divided by the number of outcomes in E. Now, looking at how this affects probability. Example 1. Suppose that a single card is drawn from a standard 52 card deck. What is the probability that the card is a heart? Well, first, there are 13 hearts in the deck, 52 cards. This implies the probability of heart is going to be 13 divided by 52, which is a decimal, is 0.25. Now, B, what is the probability that the card is a heart given it is a red card? Now we have the condition. We know it's a red card. Now, what's the probability it's a heart? Well, first off, there are 13 hearts, 26 red cards. So if we know it's a red card, we're only dealing with those 26. So the probability of heart given red is 1326 or 0.5. You notice the probability doubled. Now, example 2. Suppose that a single card is drawn from a standard 52 card deck. What is the probability that the card is a king? Well, first off, there are 4 kings out of 52 cards. So this implies the probability of a king is going to be 4 divided by 52, which is 0.076923077 if you use your calculator. What is the probability that the card is a king given it is a face card? So now we know there are 4 kings in the deck, but how many face cards? Well, there are 12 face cards. So the probability king given it's a face card is going to be 4 out of 12, or 1/3, which is 0.3 repeating. Now you notice this changed the answer drastically again. So the conditional probability will usually increase your probability. Now, general multiplication rule for dependent events. The probability that 2 events E and F both occur is the probability of E occurring times the probability of F occurring given the occurrence of event E. So if we look at this, so the probability of E and F occurring is equal to the probability of E times the probability of F given E has occurred. Example, suppose 2 cards are drawn from a standard 52 card deck without replacement. What is the probability of a king and queen? Now we're not putting the card back in, so this makes it dependent. Okay? Now, probability king and queen. So that's going to be the probability of a king times the probability of a queen given the first card was a king. So the probability of a king is 4 52nds times. There's still 4 queens in the deck, but there's 1 less card, so it's 4 out of 51. Now use a calculator, multiply this, we get this answer, 0.006033183. Now, note on using your calculator, okay? A lot of times people do it in pieces. We should do this all as one problem. So you could take 4 divided by 52 times 4 divided by 51, then hit your equals, and you will get it in one sweet problem. Okay, example 2. Suppose 2 cards are drawn from a standard 52 card deck without replacement. What is the probability of 2 queens? Again, drawn without replacement means they're dependent. Now, probability queen and queen equals probability of queen times probability queen given the first card was a queen. So it's 4/52 times 3/51. Now this time, the number of queens went down 1, the number of cards went down 1. So that's where you get the 3/51. To multiply it out, we get this answer. Now, how did this example differ from number 1? In this case, we were looking for 2 queens, so there's going to be 1 less queen and also 1 less card. Example 3. Suppose that of 100 circuits sent to a manufacturing plant, 10% are defective. The plant manager receiving the circuits randomly selects 2 circuits and tests them. If both circuits work, she will accept the shipment. Otherwise, the shipment is rejected. What is the probability the plant manager will accept the shipment? Okay, so now we want to check the circuits. So what's happening? First, what does it mean to accept? It means that both circuits good. Second, how many are good? Well, 10% are defective, so that means 10 out of 100 are defective and 90 out of the 100 are good. Third, sampling done without replacement implies dependent. So hence, what am I looking for? I'm looking for the probability good and good. The first one's good, the second one's good. So the probability of good times the probability of good given the first one was good. So that's going to be 90 over 100 times 89 over 99. Because the first one was good, that's 1 less good, 1 less circuit. And we multiply it out, you get 0.809090909. Whenever small random samples are taken from large populations without replacement, it is reasonable to assume independence of the events. As a rule of thumb, if the sample size is less than 5% of the population size, we treat the events as independent. What this means is if you calculated the probability as a dependent and you calculate it as independent, they are going to be very, very close. So if the sample size is small, it won't matter whether you use independent or dependent. Two events E and F are independent if the probability of E given F is equal to the probability of E, or equivalently, if the probability of F given E equals the probability of F. If either of the above conditions is true, the events are considered independent, and the probability of E and F equals the probability of E times the probability of F. Okay, this brings us to the end of section 5.4.